Thanks a lot. And I guess the goal of this talk is to also explain the title and the picture that comes with it. And I should, oh goodness, yeah, sorry, this is somehow, right. This is the next slide down here, so don't, try to not be distracted. It's exciting to be able to present this here because really the core of the idea happened 6 years ago in the summer here between my first year at IIS and my second year at IIS. So somehow without these 2 years, I don't think any of this would be happening. And to put things in perspective with the present sort of concentration on symplectic geometry and dynamics, somehow, you know, I think what we're asking there is sort of what could holomorphic curves tell us about dynamics? And then maybe at some point we're going to ask, why do they tell us something? So somehow the area that I'm thinking about is more, we know that holomorphic curves do something about low-dimensional topology. And we know technically how. And I'm going to try and explain why. So why do holomorphic curves actually help us do low-dimensional topology? And there's, of course, answers on a couple of levels. And so I'll try to give you the answer that essentially holomorphic curves give us a categorical structure, which I'll introduce, that sort of very well fits with decompositions in the topological category. So that's the plan. And all of this is joint work with Chris Woodward at Rutgers, whom I'm acquired as a young postdoc at IIS. And when there's anything on chain level, it's joint work with Sikimeti Mao. So let's see, introduction. This is not pretty. All right. I'm going to need to make do with the cursor that is. All right. Ah! All right, that was a little quick. Let me recap. All right. In the 80s, Alan Weinstein sort of introduced this mantra that in symplectic topology, really everything is phrased in terms of Lagrangian manifolds, submanifolds, and I'll say what that is. And Gromov introduced a very powerful tool, namely pseudo-holomorphic curves. And then in the 90s, somehow, there was a conjecture somehow tossed around between Atiyah and Floer, and also Oshwart and Szabo actually proved theorems that somehow do magic with pseudo-holomorphic curves in order to produce topological 3-manifold invariants. So the overall sort of approach in both of these sort of topological theories is you take your favorite, you want to sort of associate a group or maybe a group modulo isomorphism to a 3-manifold. So you're going to chop it apart into 2 handle bodies along a surface. That's depicted here. I've also kept track of the circles on the surface that contract in one or the other handle body. And some way or another, this data gives you a symplectic manifold for the surface and a Lagrangian submanifold for each of the handle bodies. So the easier and sort of more commonly known one at this point is the Oshwart-Szabo variant, where you take the symmetric product of the surface to get the symplectic manifold, and where these attaching cycles give you Lagrangian tori. So they are half-dimensional subsets, at least. And I'll say a little about what that means to be Lagrangian. The sort of Atiyah-Floer side did something very similar, just on the level of representation theory. So we're taking representations of the surfaces and representations of the handle bodies. And in theory, you can do this in any other group or more interesting bundles. So there's sort of a larger space to play with here. All right, so that's how you get from a decomposition somehow into something symplectic. All right, so what essentially happens here is there's some dimensional reduction of a gauge theory going on. And then you have to throw this into a big black box that says Floer homology on it, and requires a lot of work, namely counting pseudo-holomorphic curves, but you get out a group. It sort of comes from this pair of two Lagrangians. It has something to do with the intersection points of these two half-dimensional submanifolds. And I'll say more about that. But then the magic is, somehow, the claim is that this is a topological invariant. So, in particular, it does not depend on the choice of the splitting. So I could split on a surface of much higher genus. I would be looking at, the intersection points are the same, but I would be looking at, or can be identified, but I would be looking at holomorphic curves in a completely different manifold. So the question is, why are the two groups still the same, modular isomorphism? And so that was proven by Oswald and Szabo by something that I think is just, that was just magic. We really sort of needed to understand very explicitly what the curves are. And it wasn't proven for TR Floer conjecture. In fact, that was my thesis project, and I did something different with it. So what I think we can say now is that, so this is a recap again of this magic. The reason that this is well defined is that there is a functor going on here from a cobordism category to a symplectic category. And then there's a two-category structure on the symplectic side, and this is just a morphism space in the two-category. So I'll get back to that. But so nowadays, I think really you should think of your three-manifold as a cobordism from S2 to S2. So I'm supposed to take out little neighborhoods of points. And if this thing is connected, it doesn't matter where I take them out. Right? So then I can view this as a morphism in a cobordism category. And then what I've done here is just I chose some decomposition. Right? But if this is a functor, then different decompositions here go to somehow, I mean, different decompositions of the same morphism should go to different decomposition of the same morphism on the symplectic side. Right? So what I'm going to need is some way of saying that some decompositions here are the same categorically. All right, so that means I need to talk about two categories. So when I was last at IAS, I would have walked away from anybody who told me I needed to know about two categories, because I thought I'm an analyst, I can do topology by doing analysis. And I still can, but the best way to explain it really is to talk about two categories. So something I learned here. So, and of course, this is sort of reverse engineering history somehow. Only after we wrote the whole paper, I realized that there was something that's called string notation in two categories. And it looks like quilts. And so I'm going to explain the string notation first, and then I'm going to explain what quilts are. This is not the way we came up with it, but I think it's the right way to explain it. So, and the right way to understand string notation, I think, is to think about the topological category in 2 + 1 + 1 dimensions. So I'm going to try and explain all of these things at the same time. So let's see. A two category, and there's two examples. So the category, there's a two category whose objects are categories, whose morphisms are functors. And there it really makes sense to somehow draw them as maps. Right? And whose two morphisms are natural transformations, that also really makes sense to draw them as things that somehow intertwine two maps. Right? And then we need to make sense of composing horizontally, so I need to compose morphisms. But I should also, since I have two morphisms, the composition on the level of morphisms should become a functor, so I need to make sense of this picture And I need to, these are morphisms in the category of morphisms. And so I need a composition on here, so I need some vertical composition of these natural transformations. All right. So on the topological side of things, that's the reason I've called this sigma. There's sort of a dual notation of these things. Here you kind of think of a point labeled with sigma and an arrow maybe labeled with the morphism. And then sort of the area between two arrows is labeled by a two-morphism. Right? So in the string diagram, it goes the other way. A two-morphism gets associated to a point, and an object gets associated to a little square patch. The reason is that all these pictures here really tell you how to build a piece of four-manifold. Right? So if you just have an object, a surface, you can build a piece of four-manifold by taking this little patch times the surface. Right? And if you now have a cobordism between two surfaces, and you already have these two pieces of four-manifolds, patch times surface, patch times surface, what you got to do is you glue in along an interval your cobordism. Right? So it makes a whole lot of sense to sort of label, to draw this horizontal arrow and label that with the morphism between the two objects. And then I don't really need to tell you what a four-dimensional cobordism between two cobordisms is. I can just say it is whatever you need to glue in here to make this a closed, smooth four-manifold. No, not closed, locally, right? So make this sort of a smooth piece of four-manifold. Right. So, and in that sense, so once I have the string diagram notation, I need to make sense of pictures like this. Right. So that's sort of the associated algebraic compositions that I need to somehow define, right? So somehow this should be a new two-morphism. Right? But in the topological category, that's very simple, right? You glue everything together, what are you going to get out? Well, you know, that looks like a piece of four-manifold that has, you know, the right boundary strata to be a cobordism again between the right things. So, and the beauty of the string diagram notation is somehow that you don't need to write down a long list of algebraic axioms now. You can just say, whenever you draw a string diagram with, you know, some more lines and points, it should make sense. And so, what do I mean by that? So here's the example of the main axiom in two categories. It says something about it, right? If you write this down algebraically, it says that somehow vertical and horizontal composition are sort of interchangeable. But as a string diagram, it just says when you draw this picture, it makes sense. And by making sense, I mean, right, you can make sense of it in two orders. You can first cut along the green side, and then you see that there's some vertical compositions of the two morphisms. Right. And then you're doing a horizontal composition. Or you could cut along the blue line, and first you have a vertical thing, and then the horizontal one. And when you think about the topological category, right, this is the same four-cobordism, no matter in which order I glued things in. Right? And that's the proof that top 2 plus 1 plus 1 is a two category. Right, so in terms of string diagrams, it's sort of very nice and intuitive. You know, there's, of course, some technical issues that you might want to worry about, smooth structures, but just sort of the overall structure is sort of very nicely somehow captured in these string diagrams. And that means I could now also, I'm going to sort of use this language of string diagrams to try and give you an impression of how we make a symplectic category. Right. So that means, let me go back a page. So I want to tell you what a symplectic 2 category, what our symplectic 2 category is. Right. So that means I need to tell you what the objects are, what the morphisms are, what the 2 morphisms are, and I need to make sense of these 3 kinds of pictures. Right. Or general kinds of pictures with, you know, patches and lines between them and these punctures. So, questions up to here?
So when you're drawing these pictures here,
yeah.
the place where you're gluing it is not the surface, right? It's the patch. Is that what that means?
Where I'm drawing. So this picture here, right? So, okay, so what would this picture be? I've neglected a couple of things, right? So there's this patch here somehow has a trivial fibration with sigma naught over it. Right? And there's another patch with a trivial fibration by sigma 1, sigma 2. And then I need to somehow glue these 2 bits of 4 manifold together. And so along this common, I mean, there's this piece here has a line times the surface as boundary condition, as boundary. And there's a line times the other surface. And I'm going to glue them together by gluing in the line times the cobordism.
And you're regarding the surface as the fiber then?
Right. Yes. Yeah. Here somehow this is not a good picture of a in a way. Yeah, this is not a good picture for a fibration, right? Because the point over this here is a surface. Sorry, the fiber over an interior point would be the surface, and somehow a fiber over this point on this line would be a cobordism. But I could view this, I shouldn't think of this as a fibration, I should think of this as a sort of gluing procedure. Right? Because then also, I mean, there's a piece of 4 manifold that gets glued in here. And it's sort of the fiber over a point, but it's really, the gluing procedure. Yeah?
I'm still confused what such a picture means. It means the data of object morphing to morphism with some compatibility in the 2 categories.
So when you see a string diagram, it really actually is a picture of a 2 morphism. So I think that's maybe.
But between what and what?
Right, so let's see. Right, so you see this line here is an interval times a surface. And here's an interval times another surface. So there's 2 objects, sigma naught and sigma 2. And along here, if you read along the bottom line, you see a morphism from sigma naught to sigma 1 and a morphism from sigma 1 to sigma 2. So you should think of composing these 2 morphisms, right? Then you get a morphism from sigma naught to sigma 2. So in this case, that's a 3 cobordism. Right? There's a 3 cobordism down here, and there's a 3 cobordism up there, and they have the same boundaries. Right? And the whole picture gives me a 2 morphism between the bottom morphism and the top morphism. Right? Yeah, so there's we can make this all precise. So there's a little sort of language involved in saying how I should read these. Okay, so let's see whether I can convince you that there is such a thing as a symplectic 2 category. So, well, our objects should be symplectic manifolds. And I'm sort of assuming that people have all seen some definition of a symplectic manifold at this point. What I'm mostly interested in is, well, I will want holomorphic curves to be a well-posed PDE, so really I mostly care about some compatible, almost complex structure going on. I don't really care right now. It could be infinite dimensional by me for the objects. But now when I'm, right, so now I need to make a quilt. Sorry, I need to make sense of this first string diagram. Right? So I should make sense of a two-dimensional patch labeled with this symplectic manifold. And what I do is, well, I do what Gromov did. I put a complex structure on the patch. Think of it as S and T coordinates. I'm looking at maps into my symplectic manifold that satisfy dsu plus j dtu equal to 0. And so now if I want to say that this is a Fredholm PDE, I should probably assume that M is compact, or at least finite dimensional in some sort of geometric bounds.
And when you say symplectic, it is symplectic plus the pseudo-holomorphic plus the pseudo-complex.
Sorry, every symplectic manifold has a contractible set of compatible almost complex structures. So because it's contractible, it's never going to matter. Up to, right, on homology level, it's never going to matter. So, yeah. Right, I will secretly always choose a complex structure, and then I will not tell you how we prove that things don't depend on that choice. They won't. So, it's the symplectic form that governs all the invariants.
Never will need J to be general, because then it's no more simply connected.
Sorry?
If you put on J some condition of general position, then the space of J is no
Oh, it's no more connected. Right. I can't do that, right? Because then right. Yeah. I mean, there is big, we do need to wiggle on the J usually to cut out our moduli spaces transversely, and that's a topic for another whole rant that I hope to give you at some point. But yes, I will sweep all of that under the carpet today. So, right, so for now, let me just say I'm fixing the J. And then this is locally we have some elliptic estimates for this PDE, and we're fairly comfortable that we can make some moduli spaces of solutions out of this. So I haven't really told you how this string diagram defines a two-morphism. I've just told you how to get a well-posed PDE out of it. So I'm going to get to the two-morphism all in one go once I've told you what two-morphisms actually are. Right, so for now, I'm just going to make PDEs. Right, so the next thing is morphisms, right? Between two symplectic manifolds M and N, I should tell you what a morphism is. And that's following Alan Weinstein. We would like this to be a Lagrangian correspondence. Or right, I should really have used the word relation. Because what it is a relation, namely a subset of the product. Except we wanted Lagrangian, so that means when I take minus the symplectic structure on one factor and plus the symplectic structure on the other, I get a submanifold on which the symplectic form vanishes. What really is important for me is that this means that the tangent space of L is also normal to J times the tangent space of L. So it's totally real in the almost complex structure. The reason I've reversed the sign here is that we would like symplectomorphisms, that's the second dot here, to be an example. Right? So if I have a diffeomorphism that preserves the symplectic form, I would like the graph of that to be a Lagrangian. And that requires this reversal of symplectic form here. So that's one silly example. The other silly example is somehow the opposite of a graph. It's to just take the product of two Lagrangian manifolds, one in M0, one in M1. So that's somehow the opposite of a relation. So if the two sides don't talk to each other, right? There's no. Right? The point here has to lie in L0. The point here has to lie in L1. Yeah.
I have a question about the stuff you said you would sweep under, right? So the J there is,
yeah.
You said you have to perturb the J
Mm-hmm.
to get transversality or whatever. like the one you wrote?
The split form. We claimed that, and then we burned in hell for a year last year trying to actually prove it. But it just got refereed very, very carefully, and I'm pretty confident in saying that we actually proved it. But we used Sartre's Mail theorem countably many times, over countable sets. So it's an atrocious proof, but yes. Yeah, we essentially proved transversality by asserting that that in every set of cows, either all cows are gray or none of them is gray. Which is fine when you're talking about a set of cows that's 0 or 1 element, right? But, yeah, somehow, yeah, that slipped by all referees and ourselves. Yeah, we dealt with other sets of cows recently. So.
But that is for M under some conditions, like.
In the transversality, I really don't care about compactness. So. That doesn't mean I can prove compactness. So, but I can get transversality in general for the Floer theory. So, but that's right. That's for the specialist seminar, I think. So, yeah. We only deal with compact Ls. I would really like to be quite adamant that all my Lagrangians are compact. In fact, there is, you really need a special setup for Floer theory if you want non-compact Lagrangians, and I will not make any statements about that. Right. Sort of the really more exciting example of a correspondence, and the reason I think that Alan Weinstein said everything is a Lagrangian, is that symplectic quotients are examples of Lagrangian correspondences. So those come from Hamiltonian group actions. So let me not say this in general. Let me just give you the example that I actually also want to use for an example in a moment. So one example of a symplectic quotient is if you take as one symplectic manifold C2, and your other symplectic manifold is going to be CP1. And there is a 3-sphere in C2, which has there's an S1 action actually on C2 that preserves this 3-sphere. This is in fact the Hopf vibration. And then the CP1 is S3 mod S1. And the Lagrangian correspondence is, so there's a morphism from here to there that's essentially, so let me call this, what's going on here? So I take the inclusion into M times the projection by this S1 action of this S3. Right, that includes into C2, and that projects down to CP1. So it's a 3-sphere that sits in this 6-dimensional symplectic manifold, and it is, we define our symplectic structure on CP1 exactly so that this 3-sphere is Lagrangian. So that's right, and so that's the exciting example of a correspondence, because it gives us a correspondence between C2 and CP1. Right, so now I have morphisms in this category between symplectic manifolds of completely different dimension and topology. All right. So now I have examples of morphisms, and I need to tell you how to make sense of the string diagrams. Oops. There. Right. So this is my usual colloquium talk, but I've updated it in one point where I thought really in this audience, I should not be lying about Floer homology. So I added equivalence classes here and a little more. So, oh, goodness. What am I? Oh, right, I did not. Hold on, what's happening? Oh. I should be telling you, before I talk about two morphisms, I should tell you about morphisms here. So morphisms, again, it's the same top. And now I need to make sense of this string diagram. Right. So that means now I have two-dimensional bits. And there's a line labeled by one of these correspondences. And I need to turn this into a PDE. Right. And so somehow, all right, so if I have, I'm going to draw these separately. There's a bit of a patch here, and there's a map that should go to C2. And there's a map from here that should go to CP1. And what I'm going to do is I'm going to ask this boundary component to map to the S3. So that's a codimension 1 boundary condition for the Cauchy-Riemann operator, which is, underdetermined totally, right? I should have half-dimensional boundary condition, something totally real. So this is not a good PDE by itself. And what's also not a good PDE by itself is to take a holomorphic curve in CP1 and completely determine what its boundary condition should be. Namely, I'm going to ask V on this boundary to be equal to the projection composed with U on its boundary. All right, so this is a map to S3. I can project that to CP1. That's totally overdetermined. Right. But what I can do is I can think of the two together on a small neighborhood of this. I can think of this as sort of folding it over U and V, and I should reverse some signs, mapping to C2 times CP1. And then, let me call this W. Then I'm just looking at d bar W equal to 0. And I'm asking this boundary to lie in my Lagrangian. And that's now a totally real boundary condition for a Cauchy-Riemann equation, except it's in the product. So this here is totally fine and well posed. So that's an elliptic boundary value problem. Right. So locally near these lines, I get some well-posed PDE. I get elliptic estimates, except they mix the two patches. Right. Yeah. Right.
Now, there's this strange fact that for the definition of map,
yeah.
the map from M to N is the same thing as the map from N to
Correct.
N. Is it the same?
Yeah, there's no direction here, right? There's, yeah. So somehow all my morphisms are, I can transpose them, but that doesn't mean they're invertible, right? So.
And now, with what you just said, what kind of compatibility between the two pseudo-complex structures do you need?
Nothing, yeah. So I can take a J here and a J there. If I take the product J, it's going to be compatible with the product symplectic forms. And that was sort of Sopan's question before. It's like, once you deal with a J in a product manifold, somehow usually, in symplectic topology, we need to wiggle on the J to make our moduli spaces cut out transversely. And it's really not clear that we can keep a product J. And so we had to sweat for that. But sweat we did, so. So I hope this is the hardest point in this talk somehow, and it's sort of also, it's the one, I mean, in some sense obvious, but also deep and beautiful idea is that locally this PDE makes sense. And then we can do funky global things with it. And I think the place to really understand it is C2 and CP1, because you see that from one side it's underdetermined, from the other side it's overdetermined, but in the product it's totally fine. So, yeah.
Do you think of this pair UV as being defined on a half plane?
On a small neighborhood of this seam. So here, yeah, I'm only talking about PDEs locally. Yeah, only ever locally. Yeah. Yeah. So.
Here, to make the picture, you use that you M was embedding in one side and projecting into the other. In general, you need to give a lifting of this between lines.
No. So in general, right, this is a little bit of a mess. It's not M, it's this S3 here. Right? And I took this S3 and embedded it into one side and projected it to the other side. But really, that's just one example of a submanifold of the product. So all I need is a submanifold. That's Lagrangian.
The definition B of the differential equation. You cannot just, or you just map.
Yeah. So I just ask. So here's sort of the general setup. Right, I just have this, so I should, right, so language is I call these pieces patches and the line in between I call a seam because really you sort of sew them together by this correspondence. And so this is just a submanifold. I'm looking at holomorphic curves parameterized by these two patches. And along the seam, I view U and V restricted to the seam as a pair mapping to M times N, and all I'm asking is that the values actually lie in this submanifold. So at no point do I need to assume that the Lagrangian is somehow surjective on one side or injective to the other. Okay, so we have a sort of locally something that looks like a good PDE, so we can hope to build well-behaved moduli spaces out of this. All right. Ooh, things are jumping around. Okay, so now we actually get to two morphisms, and I think in the interest of time, I'm just going to mumble a little faster. So, so I'm going to lie and say really a morphism. So I should say what a morphism between two correspondences is. So there's symplectic manifolds M and N. I have two Lagrangians in the product, L and L prime. And a morphism is essentially just an intersection point of the two Lagrangians. Except I generate a complex and define a differential on it and take the homology and whatever. So let's think of it as an intersection point. And so then again, I need to make sense of a PDE. And now what I'm going to do is I need to sort of, conformally it's all the same. But in terms of sort of Sobolev spaces that I set up, I'm thinking of this as an infinite end. So I'd rather like to think of this as a cylinder coming out at you, and somehow these two lines you see, sort of two parallel lines on the cylinder. And so towards infinity, everything should become constant. So essentially, I should just converge to a point. All of this side should converge to one point in M. All of this side should converge to one point on N. Clearly, I have the two boundary conditions. So this, where U times V on this sort of pink end should converge just to this intersection point of L and L prime. And again, this is sort of, we knew this for a while, that this is an okay, in some sense, elliptic PDE, or an elliptic sort of, it's not a boundary condition, it's an asymptotic, it's a well-posed asymptotic condition for holomorphic curves. So, all right, so now we've turned all the string diagrams into somewhat okay PDEs. And so in order to turn the okay PDEs back into two morphisms, I need to tell you how a string diagram defines a two morphism. So what I do is I view this diagram. I've made sense of this puncture. What I haven't made sense is the outside. I think that's what Alex also asked. Right? So what am I thinking as conformal structure on the outside square? And I'm thinking of this again as a cylindrical end, as a puncture. So really I'm putting all my string diagrams on the sphere. And this is sort of infinity, the outside, or the North Pole. Right? And then what I can do is I can count. So for every given intersection point on the outside, Q, I can count my solutions of my PDE that on the outside converge to Q. And I can hope that this is an integer or maybe a rational number or something and multiply it with Q. And I'm getting some formal sum in intersection points. Right. So that's how I make my two morphisms. Yeah. No? There's a lot of technicalities I'm not talking about here, and I think they might be for coffee. So maybe, right, since we have it here, so now there's more technicalities. I should prove something called gluing laws, and that's where we used Sekimeti as grad student slave laborer. And then the gluing laws for quilts really are the ones that tell me that all the larger string diagrams make sense. It doesn't make sense in which order I degenerate them, in which order I sort of cut them apart to turn them into algebraic maps. Yeah. Yes.
What do you mean by Q belonging to the intersection
of the outside? Right. Yes. Well, okay. That's one thing I tried to slip past you. It didn't, so all right. So here's this example, right? So I should think each of the y's actually is now a Lagrangian. So each of the sigmas is a symplectic manifold, and each of the y's is a Lagrangian correspondence. So then if I look at this outside here, I have 4 Lagrangians, right? 1, 2, 3, 4. And I can pair them up. So it's 4 Lagrangians, and I have 3 symplectic manifolds. Sigma naught, sigma 1, sigma 2. But I can pair these up if I take 2 copies of sigma 1, because really when I go around, I see sigma 1 twice. Right. So I can pair these up, appropriately and exchange factors to make 2 Lagrangian submanifolds in sigma naught times sigma 1 times sigma 2. Right. Or differently put, really what this is, it's sort of a cyclic correspondence, right? I start at a symplectic manifold, I keep going through arrows in my category, and I end up here again. And there's a notion of a generalized intersection point for a cyclic correspondence. Right. So somehow the stupid example is really, right, if you have a Lagrangian in M and another Lagrangian in M, I would think of it as a cyclic correspondence from a point to M and back to a point. And there's a sense in which there's an intersection point of this. And my claim is I can, generalize this to longer cyclic situations, right? And there were some primes someplace. So here a definition of intersection point would be a point here and a point there that lies on this morphism and that lies on that morphism. Right? And here it's the same definition. I should take a point in each of these that should satisfy all these matching conditions.
So point is actually multi-point.
Yes, a tuple, right, yes. Yeah. And that's also exactly what you want as asymptotic condition at infinity. Right? Here there's no reason that this point in sigma 1 out here should be the same point as out there. But as an asymptotic condition out here, I should converge to all the same. All right, so excellent. Okay, good. So right. Here's an example of why we need gluing laws, but I'm not going to talk about that. The one thing I sort of slipped past now is I didn't really say anything about horizontal composition of correspondences. Right? So there's this picture here that should be equal to the horizontal composition of these two correspondences. So there's a submanifold in M0 times M1 and one in M1 times M2. And somehow by just sort of going through the PDE version of the string diagrams, I've sort of made a stupid definition of a symplectic category probably, where really I've enlarged my morphism space by allowing sort of these two-step correspondences. So I view this sort of sequence of arrows as just another morphism. I'm kind of just a little afraid of composing them, so I'm just not going to do that. And whenever I see a line labeled with this two-step thing, I'm just going to plug in a strip in the middle. So that's somehow the silly part of the theory. And that's somehow something one can simply do. So now in order to actually do something topologically relevant, somehow the composition in our symplectic category should be related to the composition that you do on cobordisms, right? So thinking back about the representation spaces and the symmetric products, right? I should think about what actually happens to my correspondences when I glue two bits of cobordism to each other. Right? So I like to think about representations more. So, right, so I have for each surface, I have a representation space, and I should think of this really as a flat connection on the surface modulo some gauge equivalence, right? And then when I have a cobordism between two surfaces, really what I'm taking is I'm taking flat connections on the three manifold, and I'm restricting them to the boundary, to the two boundary components. Right? So that gives me a subset in here, and whether or not that's a nice space, depends on your particular setting. Right? But now if I do the same thing on a larger cobordism, right? So if I have a cobordism now between sigma naught and sigma 2 that is of these two pieces, right? Then there is a natural composition that I should use. I should take the flat connections on the whole cobordism and restrict them to the two boundary slices, right? Which means really what I'm doing here is I'm taking a flat connection on y0, 1, flat connections on y1, 2. I'm asking them to restrict to the same thing in the middle, right? Because otherwise they're not going to make a flat connection on the whole thing. And then I'm going to completely forget everything in the middle. I'm just going to project to the boundary values. So intersecting with the diagonal is asking, right, to match up in the middle, and then I project to the two outside components. Right. So, well, this is the right thing in gauge theory as a composition. It's also the right thing if the Lagrangians are graphs of symplectomorphisms. Right, then this is a very fancy way of saying I'm composing the two maps. And it is troublesome if you stick in general Lagrangian submanifolds. Because there's two things that Lagrangian submanifolds don't like. There's an intersection going on here and a projection. Right? So it can get totally singular. So there's a little bit of symplectic linear algebra makes it not so bad as if once I wiggle a little, this intersection will be transverse. And once it is transverse, the projection actually gives us an immersion that's Lagrangian. It's still a little scary. At least I don't like to try and do holomorphic curves with immersed boundary conditions. And actually, categorically, I think it's wrong to do this composition. But it's there, right? So we should do something with it. What we do with it is that we prove that somehow if it's a nice composition, then it actually is the composition in our 2 category. Right? So we're saying if this intersection is transverse and if the projection is an embedding, right? So if really my geometrically composed correspondence is just an embedding from the upstairs, if I have this nice lift back up, and I need to, so now I'm going to need to really restrict my choice of symplectic manifolds in order to make sure I don't get singularity formation. But assuming I can exclude the fun that is bubbling, then sort of this horizontal composition that was just this 2-step sequence, which is sort of a silly morphism in our category, will in our 2 category, right? In a 2 category, I can talk about morphisms being isomorphic. Right? So then this morphism is isomorphic to the geometrically composed guy. Right. Phew. So let's see. So the proof is that's where the analysis sort of goes in. Right. So essentially, on the level of these string diagrams, I need to somehow identify this PDE here that has 3 bits of holomorphic curves with a PDE that just has a holomorphic curve in M0 and M2 and a boundary condition on this submanifold that I got from this geometric composition. And I do that by taking the width of the middle strip very close to 0 and then prove a lot of estimates to show that really there's a 1-to-1 correspondence between these solutions. And there's a singularity formation problem that you can, most of the bubbling in holomorphic curves you can think of as actual blowing a bubble in your bubble gum. So, this is sort of a sheet of your bubble gum, and some evil person comes in and blows a nice sphere out just as you're shrinking the strip towards 0, and then depending on how fast that person blows and where exactly you blow into this sheet, you're going to see one or more of the seams on that sphere that bubbles out. And if you just see one seam that's been dealt with, or if you see no seam that's also been dealt with, the case of 2 seams is new, and that sort of locally, if you sort of look at the point at which the node appears, that is not a well-posed PDE yet. So that's something that I've also found a little too scary to deal with at least 5 years ago. But I knew a trick. So there's a trick which I should unfortunately not really get into. Yeah. Yes. In fact, they are not isomorphic. I have tons of examples where there's no way they will be isomorphic. Yeah. Figure 8 bubbles do exist. They do happen. It is not right. So this is actually, I don't know. Kenji Fukaya sent Mohammed Abu Zaid back to me with the homework of proving that bubbles are actually codimension 2. They are not. So and you can see this by realizing that you cannot twist before gluing in because of the direction of the two seams. So they do happen codimension 1. They give you boundary conditions, boundary effects, and no. Yeah. Wishful thinking. Yeah, I mean, in many cases we can exclude them, but there's also there is going to be some A infinity functor with some abstraction term that comes from counting the bubbles, right? That's also what Kenji has actually taught us, that if d squared isn't 0, it's not 0 for an interesting reason, and there's a larger algebraic gadget. So we'll sort of need to describe that. But so let me just flash this by. There's a standard mean value inequality for sort of for nonlinear sort of Laplace equations. And you can do a nifty little proof by contradiction that somehow says, if I get a singularity, then at that singularity, some minimal amount of energy has to concentrate. And so I'm just going to not exactly look at what happens when the energy concentrates. I'm just going to somehow get myself into an assumption in which I know that energy can't concentrate. Yeah.
You are telling that in general one should define morphism in the category as formal composition.
Right, yes.
But then you need to define what is a morphism from one such composition to another, even to make sense.
Right, yes. Yes, and you can do this by taking generalized intersection points like this, and there's something called a quilted Floer homology, which I'm also sweeping under the rug here. So there's somehow nothing really deep happening there. You just.
In good case, will there be a unique isomorphism between the composition and the formal composition?
Only if you tell me in which order you compose. Then there is so the isomorphism between one of these morphism spaces and the other depends on the order in which you compose the morphisms, but nothing else. It doesn't depend on the J or any other choices, but it depends on this order, and that actually very interestingly reflects the recent naturality problems in Heegard-Floer theory. So.
It's normal if you give out the order.
Right, but the claim is essentially in Heegard-Floer theory is that it doesn't depend on the order. Yeah. And I think we can also prove that. But you need. No, and Heegard-Floer theory is just sort of the realization of this whole program when you take a symplectic manifolds, the symmetric products of surfaces. So what you essentially just asked is whether my three-manifold invariants are groups or groups modulo isomorphisms. And so far, I'm only explaining that they're group modulo isomorphisms. But when you would like them to be groups, you need to ask about this naturality. Okay, good. So I should wrap up with the theorems. So this bubbling problem is the reason that I'm writing monotone or exact here. So for now, I need some pretty severe assumptions on my symplectic manifolds under which I know that once energy concentrates, there cannot be any more solutions, essentially. But once I have that, then I can build a symplectic 2 category in which contains all monotone symplectic manifolds, all monotone compact Lagrangian correspondences, contains more morphisms, namely these sequences, and in which geometric composition of these correspondences, when it's nice, actually is the composition. So I've sort of taken the natural pieces that we want, and I can sort of thicken it up to a 2 category. So that's this guy. And then at some point we prove the corollary of this. But I recently learned that when you have a 2 category, it automatically comes with a 2 functor from the 2 category to the 2 category of categories. All you need to do is you need to pick one object in your 2 category. And in this case, the obvious object to pick is the point as a symplectic manifold. And then magic happens, the natural 2 functor that you get is very closely related to the Fukaya category, which we know is interesting from mirror symmetry. And I'm not going to say what we do on chain level, but what this means is now if I have a functor from a topological category into the symplectic category, I can just compose it with my functor from symp to cat. Right? So somehow this is the proof of this corollary is totally stupid. I have a functor from the 2 functor from the symplectic to the category of categories, and hence if I have a functor from here to there, I get one from there. Yeah. So
What was
cat is a category in this case actually whose objects are categories and morphisms are functors. And I've actually made this statement not in the right. I could have made it in the n plus 1 plus 1, and then I should have said 2 functors. Here I'm only saying functor because the picture here is not the example of how to make 4 manifold invariants, it's the example of how to make 3 manifold invariants from a 2 plus 1 field theory. I guess there's sort of a little extra bit in this corollary. We actually just need a partial functor. A partial functor is something that is defined on all objects and on some sort of prime set of morphisms, except they're not prime. So the morphisms generate everything up to some relations. Right? So like handle attachments in the cobordism category, or in the symplectic category, the sort of smooth Lagrangian submanifolds. Right? By this horizontal algebraic composition, they generate all the morphisms. But I have this relation by the strip shrinking isomorphism on this side. Right? And on the cobordism side, I have surf moves between different decompositions of, 3 manifolds or n plus 1 manifolds. Right? And so what one needs to check, really you only need to represent the prime morphisms by your functor. And you just need to check that the moves between different decompositions correspond to moves on the other side. And so our construction of the symplectic category somehow very nicely mirrors surf theory on the bordism category. And I think that really is the reason why pseudo-holomorphic curves help us do topology, because somehow they help us have a structure which mirrors surf theory. So that is like the upshot that I can give here. So here's that picture again. Right, there's the decomposition going on. That's surf theory. You get into this cobordism category. If this is a functor, then we have a general morphism from a point to a point, right, where I pick the right thing for S2. S2 here should go to a point, right? And then I can take the 2 morphism of this generalized morphism in the symplectic category, and that's supposed to be my invariant, and it is if these arrows are So that, to me, so I feel I have now solved my thesis problem in some way. I've explained why the Atiyah-Floer conjecture should be true. So I haven't quite proven it, but I know why it should be true. So thank you.